afternoon, everybody, and welcome to Corridor Conversations on this rainy day that's turning out to be awfully nice. Um, Corridor Conversations is a joint venture between the villages along Route 1, and that includes Hyattsville Aging in Place, University Park Helping Hands, College Park Neighbors Helping Neighbors, and College Park Explorations on Aging. We do these monthly seminars by Zoom, typically the fourth Saturday of every month. And I would encourage you to pay attention to the Hyattsville Aging in Place website, which will list the upcoming events. And actually, I'll go ahead with that right now. April 27th will be our next one, and that is on Hyattsville Speaks. Jennifer Ridgway is the founder and director of Yard Dramas, and this is interesting. Carter, fill me in if I have this wrong. It's a theater, arts, and education creative learning, and what they do is take people's stories and then turn them into productions. So whether or not we will see a production, I'm not sure, but it should be a very interesting session. Anyway, we are overwhelmed and delighted today to welcome Dr. John Mather as our speaker. Dr. Mather is his bio reads I'm just going to highlight it. It's so incredible. He's a senior astrophysicist at the Observational Cosmology Lab at Goddard. And he is also the senior project scientist on the James Webb Telescope. He received a bachelor's degree in physics from Swarthmore College in Pennsylvania, and his doctorate is from the University of California in Berkeley. His research centered on infrared astronomy and cosmology. Dr. Mather has served on advisory and working groups with the National Academy of Sciences, NASA, the National Science Foundation, and the Center for Astrophysical Research in Antarctica, which is, to me, the opposite of where the Webb Telescope is. He is as a senior project scientist for the Webb Telescope, he leads the science team and represents scientific interests within the project management. He is as a winner of the 2006 Nobel Prize for Physics, congratulations, chosen by the Royal Swedish Academy of Sciences. Dr. Mather shares the prize with George Smoot of the University of California for their work using the COBE satellite to measure the heat radiation from the Big Bang, which blows my mind. Anyway, Dr. Mather, we're very much looking forward to your presentation, and thank you for joining us.
Well, thank you for the invitation. It's always a pleasure to tell these stories, and but today it's a special pleasure to see some of my most longtime friends and most delicious colleagues and neighbors. So thank you all for coming to hear the story. Some of you know some of this from knowing me forever. Some of you haven't heard the technical part before. Anyway, thank you very much for the invitation. I love talking with my neighbors. So I want to show you the story of the universe and some of how I found out about it and my small, actually, you might think it's big, but it's actually quite small role in what all these marvelous discoveries. So I'm going to show you my PowerPoint, and let's do it again here. So does that look good on the screen for you now? This should be the opening picture. By the way, is my sound coming through correctly?
Yes, you're fine.
Okay, excellent. So we're talking about the James Webb Space Telescope, the JWST mostly today, but we'll give you a little bit of the run-up to it. It's a joint project of NASA with European and Canadian space agencies. And I was the senior project scientist up until last year, and I stepped back from that so some younger people could take on this challenge of running this marvelous observatory. In the middle, you see the picture of the telescope itself as we imagine it in outer space. The mirror that collects all the starlight is a gigantic golden hexagon. It's actually, of course, not solid gold. We'll tell you more later. It's 21 feet across, which is to say in metric units, which we should be learning, 6.5 meters across. So it's taken 20,000 people to get this thing up and working, and there are about 10,000 professional astronomers in the world who are in a good place to use it. And we've had proposals from at least half of them come in already for what they want to look at. So the data become available to everyone. Some of the data right away, some of them data after a year, but you can get it all from our websites. So that's just a quick hint about what we're up to today. But why are we doing all this? Well, the questions that drive scientists, and especially astronomers and historians and geologists and anthropologists and biologists, who are we and where did we come from? So astronomers can work on part of that. We can work out the history of the universe. And we can tell you how the atoms came together to make planets like Earth. We can work on that. Eventually, we may be able to answer for you the question of are we alone by finding some neighbors. We have our opinions and ideas and guesses about that. And a particular part of that question is life a miracle requiring divine intervention or extremely rare circumstances, or is this a thermodynamic imperative which will always start whenever it's given a chance? And so currently, by the way, I think the scientific opinion is leading toward the second one, that it will always start quickly when it gets a chance. We don't know how, but we're making some progress on the how part. The evidence that we have, by the way, is that fossils here on Earth show that within a few 100 million years of getting an ocean, we got fossils of indicating life. So it took quite a long time for even that to occur. But on the other hand, intelligent life with a civilization like ours took the entire history of the universe to get here. And so we're very brief and recent arrivals on planet Earth, and our stories that we can tell because we can speak and write and read and make computers, those are probably pretty rare in the universe. So people can go to Mars. We are going to go eventually. It's harder than people imagine, but we have been making a lot of progress recently. On the other hand, astronomers, we travel very fast. We can travel at the speed of imagination. We take pictures, we make movies, we make computer calculations, we simulate what was out there, and I think I even have a movie to show you of how the galaxies grew from the earliest moments of the universe. And of course, we did not make that observation. We could only imagine it in a computer. So, who is we, of course, and who are we? Well, pretty well established now that there's a genetic component to that carries the information that sort of controls our lives in ways that we will never quite understand because it's too complicated. You can't understand what that computer is doing in front of you, and that's simple by comparison. There's a philosophical question about free will, which is really quite interestingly explored by Robert Sapolsky in his book. He's a primatologist. He studies creatures like ourselves, and he says this is actually a pretty interesting question too. So the upshot, of course, is this is a very complex world we're in. It's unpredictable. It's fundamentally unpredictable because of the incredible amount of information that controls it through zillions of interacting systems. So zillions is probably the right term. So well, just to give a perspective, we've got about 86 million neurons in each of our bodies, gives us consciousness and whatever that is. There are about 30 trillion other cells and something like 36 trillion microbes sharing our body. And we hardly even feel it. When we speak or see, we hardly can imagine those billions and trillions of things going on. And they're more or less independent agents communicating with each other, having programs to do what they're supposed to do. So this is a really fascinating story too, that will get to be even more fascinating when we find signs of life elsewhere. So a little bit of my history. This is the place where I grew up in far northern New Jersey. It is a mile from the Appalachian Trail. This is an experimental farm belonging to Rutgers University, although it isn't anymore. Um, and they raised bulls in this barn here, and they had chemistry labs. And my dad was studying dairy cows to see how we could get more and better milk. So they did. Um, my dad analyzed the records of milk production for 10,000 cows in some of the first computers that we had. So I got started on science, but not that kind of science. It was a beautiful place to look at the sky and to be enchanted with science, and got introduced at the Museum of Natural History in New York City, and the planetarium shows that got my attention. So looking back a little bit into history, well, what happens over time? 1946 is a key part of the story. Right after World War II, Lyman Spitzer, shown in this picture, was an astronomer, and he wrote a little report to the RAND Corporation, which was a defense think tank and still is. Build telescopes in space to look down and up. If you can look down, of course, you can do all kinds of things that are militarily important. If you can look up, you might be able to discover astonishing things that we would never be able to see from the ground. He even imagined that if you could find an asteroid and polish the shape of a parabolic mirror into the surface, then you would be able to observe Earth-like planets around stars like the sun. So he had a great deal of foresight, and we did eventually name a telescope after him. In about 1950, although my number is incorrect here, Sir Fred Hoyle gave the name to the Big Bang, and it has confused the heck out of everyone ever since. So thank you, Fred. You were a very creative scientist, and I think you were wrong. But at any rate, the name that you gave to the Big Bang makes everyone think of a firecracker, which is exactly the opposite of what astronomers see. So that's been pretty confusing. In 1946, I turned up. That's a little bit later. And I do not remember my childhood much. I did not have a lab notebook to write in. And I didn't even think of keeping a diary. At any rate, that was my beginning. In 1948, these two gentlemen, Robert Herman on the left and Ralph Alpher on the right, were working on the idea of the expanding universe, and they said, well, it might have been very hot when it was young. We began to know some nuclear physics from the unfortunate necessity of nuclear combat at that time. And they said, we can calculate from the nuclear physics and the idea of the expanding universe that there should be heat, and it should still fill the entire universe at a temperature of a few degrees above absolute zero. Nobody tested that prediction for a long time. And so it wasn't known that they were correct, but just to give some perspective on how important it was, 300 people came to listen to the PhD defense of Ralph Alpher. Pretty remarkable thing, considering that their work could not really be checked at the time. So what happened later? Well, here is Mars. I was a little guy. In 1954, Mars came very close to Earth. The great Palomar telescope had been built. People were hoping that finally they would see what other observers had seen. These are the canals on Mars. Well, they're not there, unfortunately. So very sorry to say, but we do actually have an idea of what happened so that people thought they were canals. There are blood vessels inside the observer's eyes, and they're more or less the same every day. So when you see Mars come and you look at it every day, you see the same pattern. So people thought, with good reason, that there were canals on Mars. But unfortunately, for science fiction, they're not. So what else happened around it was 1957, the Sputnik went up, the first space satellite, which demonstrated that space travel was going to be possible. It was not actually a surprise, but nevertheless, it got the Americans very agitated, because not only did it demonstrate that scientific things were possible, but a nuclear attack from space was also possible. So what did we do? Well, of course, we said we better fix that. So in 1958, NASA was created, and the Congress decided they'd better fund technology development for a space program as well as for all the other military things we thought we needed. So here's Jack Kennedy giving his speech at Rice University in 1962, trying to build support for the moon program. So he said we were going to go to the moon within a decade. He knew it was incredibly difficult. He said we would do it not because it was easy, but because it was hard. And he promised that we'd do that and the other things too. So it was a vision of the future, which was quite astonishing. And we've been profiting from the effort we made as a nation in those days to build up the high technology world. And we drew people from all over the world to work in our space program. 500,000 people worked on the Apollo program, which is a little bit surprising considering some other people nowadays think that it was all just a story. Anyway, that was done in 62 and 69. We landed on the moon, and I was just a graduate student putting little boys to sleep that night when that happened. So I didn't actually see it. But here is James Webb, the man. He's the one who went to the president with a plan, and he made it work. He's the man for whom we named the Great Telescope. So coming back to science a little bit, in 1929, we were just getting evidence accumulating that something strange was happening. So Edwin Hubble drew us a picture showing that distant galaxies are going away from us with immense speeds. And here it is. It's the first picture that we ever had to say there's a problem here, a really interesting result here. So each little dot on the picture represents a galaxy. A galaxy is something like 100 billion stars, like the sun, more or less, held together by gravity. And how fast are they going away from us is on the vertical direction. Far away they are from us are they on the horizontal direction. You see two things, pretty important. One is that almost all of them are going away, and that they seem to be following a trend, that the farther away they are, the faster they're going. That means the universe appears to have an age. If you run the movie back in time in your mind, you say, when were they all together? Divide the distance by the speed. In this picture, you get 2 billion years, which was wrong because the mistake was in the distance scale. But anyway, there's another remarkable thing here. There are 4 dots in the lower left corner that have negative velocity. That means those galaxies are coming toward us, and they will merge with us by and by in a few billion years. We won't be here to witness it, but whoever is here will have quite a spectacle. So 1929 recognized the expanding universe. A few years back, we realized that we should give credit to George Lemaitre as well for this. He was a theoretical physicist. He was a parish priest in Belgium. He had a PhD from MIT, and he worked on Einstein's equations. And he said, I predict this is true. When Einstein heard that story, he said that was ridiculous. On the other hand, he was right. So George Lemaitre gets now credit for predicting this. So how are you going to know what happened next? Well, I'm leaving out a lot of steps, but here is the Cosmic Background Explorer, the COBE that was mentioned in the introduction. We proposed it in 1974, which was the year that I got out of graduate school. My thesis project had failed to function properly. But when the NASA said we want proposals for new satellite missions, I told my new boss, well, my thesis project failed. We should try it in outer space. So not knowing how easy or hard that would be or how important it would be, I just said, well, why don't we do this? And he said, we'll call up our friends, we'll write a proposal. And 15 years later, it went up into space. And there it is, as we imagine it. It's probably not working anymore. But anyway, it's out there, and it measured what we hope to measure, the spectrum of the cosmic radiation to see how bright is it at every wavelength. And we made a map. Then it was followed up by 2 more space missions and many other missions to measure better. So here is the most famous thing we got from this. This is a map of the sky. So if you could see the sky and pick up wavelengths of about a millimeter, which is about 1,000 times longer wavelengths than what you can see, then you would see the sky looking like this. So these are sort of artificial colors. In this case, pink means brighter and blue means fainter. And so these pink and blue blobs are actually representing variable density in the early universe. We see the universe as it was when it was 400,000 years old, which is when it became transparent, and light from those days was free to travel without hitting anything after that. So this is the universe as it was when it was young. It has hot and cold spots, which mean density variations. And when Stephen Hawking saw this picture, he said it was the most important scientific discovery of the century, if not of all time. So now I can tell you a little bit better why that was so important to him. Number one, we would not exist if the universe had not had spots in it like that when it was young. Because our story is that gravity, acting on the denser regions, was able to stop the expansion of the material locally and pull it back into making galaxies. And galaxies could split into stars, and those could make planets. And so we're here because of those spots. Scientifically, there are also fascinating things in here. Most of the spots come from something astronomers can measure but cannot see. It's called cosmic dark matter. The pattern is affected by something else we can't see but we can measure. It's called cosmic dark energy. And if we ever do understand quantum gravity, which is still a pretty far away problem, then maybe we'd understand why these spots occurred. But right now, a big mystery. So that's the beginning of early universe, and now we should be able to see, well, what happens next. So anyway, for me personally, what happened soon after that, I showed my chart a lot, and I got to go to Stockholm to get my diploma from the King of Sweden, and I got some money which I spent on scholarships, even including some locally here in Hyattsville. So anyway, I had a good time with going to parties and speeches, and but soon I was all, well, there's a whole other story to tell. So the other story to tell is we measured to see if the story is right. So Hubble Space Telescope was launched just in April of 1990, so it's almost 34 years old, and it is still working beautifully. As you know, it was out of focus when it was launched. We've sent up astronauts altogether 5 times to improve it, keep it going, make sure it'll keep on taking great pictures, which it is. Eventually, we have to send it somewhere safe because we don't want it falling on Moscow. So we'll have to either aim it at the Pacific Ocean or push it out farther into space so it doesn't come home. At any rate, it's taking beautiful pictures. When we got it working, astronomers immediately said, well, that's great, but we still need more because this telescope, although we hoped for better, will not be able to tell you the story of the early universe. It will not be able to tell you how the galaxies grew because it happened too far back in time, and the universe was so young we can't even pick up the light that was being sent from those epochs. So they wrote a book and said, please build us another telescope. And that became this one, the James Webb Space Telescope. Here it is, another picture from our engineering drawings. The big mirror, 21 feet across, made out of 18 hexagons. It's protected by a huge, in this case, blue umbrella made of 5 layers to keep it cold. It has 4 instruments in it, cameras to take pictures and spectrometers to spread out the light from each object into a rainbow of colors, which we can interpret to learn all kinds of things, chemistry, temperature, motions, things like that. And we launched it on Christmas morning, 2021, from French Guiana. A remarkably successful venture for something extraordinarily complicated. I'll show you a little bit more about how it was done and what we've done with it since we got it up there and working. To give thanks, these are the 4 project managers that I worked with for the entire period of getting this up and running. Bernie Siri, the first, handed off to Phil Sablehouse, who handed off to Bill Oakes. So these three are all at Goddard. And Scott Willoughby won the proposal from Northrop Grumman. We selected their company to build their part of the mission. And so it's taken a team effort. These are the kinds of people that it takes to organize 20,000 other people to make the project go. Here are two of our other heroes. Our local Senator Mikulski of Maryland was a very strong backer of science, of all kinds of science, and especially NASA and NASA science. We called on her, and she called on us to fix a problem that we had. We got pretty far along with the project. In 2011, we said, we can't do it with the money that you're giving us. It was our fault. We didn't ask for enough money. And Charlie Bolden, there on the right, I was a former Marine Corps general and was currently the head of NASA. They worked together to build up the necessary support in Congress, and they got what we needed and were able to do the mission right. So thank you very much to Barbara Mikulski and Charlie Bolden. So what did we have to do? Well, we had to invent all kinds of things. I'm not going to tell you details about them, but we needed new kinds of detectors, new kinds of electronics. We needed a refrigerator to run one of the instruments at a temperature of 7 degrees above absolute zero, and so on and so forth. And we had to learn how to focus it in outer space. I'm going to skip all those details and just show you that there's the launch going up. That's a French rocket called the Ariane 5. And it looks like nighttime, but it's actually already daytime. It's just that the camera was set to pick up the rocket engines. So there it is, and perfect launch. Perfect launch to the place we call Lagrange Point 2, orbiting around that spot. These 5 places in the solar system are places where the combined gravity of the sun and the Earth will pull the object around the sun once a year, so they stay there. So we choose the L2 point there because when you put up your umbrella, the sun, the Earth, and the moon are all on one side, and you can keep the telescope protected in the dark and in the cold. So that's a special thing about that. It's about 1 million miles away from us. And of course, we don't really go all the way to the Lagrange Point 2 because it's in the shadow of the Earth, and we need the solar electricity to run the observatory. Here is our scary movie. It took about 2 weeks to do what you're seeing in this movie. First, we unfold the solar panels because we need solar electricity. Then we unfold the transmitter and receiver antenna. In this picture now, we're unfolding the framework that holds up the sun shield, the umbrella. Now we're separating the telescope from the warm part of the spacecraft. You look at this and you say it's extraordinarily complicated, and the answer is yes, of course it is. It's, as far as we know, the only way we could possibly find to measure the things we're looking at, to make the scientific observations that were called for, to answer the great mysteries that we'll tell you about in a moment. So you can see that it's complicated, and the only way you can possibly make it work is test and test and test. This part that you're watching here, the unfolding part, was tested 4 times on the ground before we believed we could safely send it up into space. This last part, unfolding the telescope itself, was simpler in a way, but absolutely essential. You just do not get to take any chances about something this big and this complicated. There is no hope of servicing it or repairing it anytime in the near future. There is actually the possibility, logical possibility long-term, that we would be able to go up with a spaceship and fix it, but not now. So how do you get this thing to work? Well, there's a lot of philosophy about this, but the basic story is John Mather's opinion that it's going to work has no effect. We have to do it right or else. So we're not very good at understanding risk. My friends have fallen off ladders, so don't you do it. Um, so it's a reminder that what you think you can do is not always what you should do. I've had some scary moments where I was the boss and people trusted me, and I realized I had made a mistake. So we at NASA, when we want to really make sure, we have people check our work. And so that's just a short summary of how do we do something so complicated. Now I want to tell you about the things that we saw. Well, number one question is, why are you building this kind of telescope? We wanted to study infrared light. Infrared light is the same as ordinary light, except the wavelengths are longer. So light's a wave, mostly. It behaves like particles sometimes, but light's a wave. And so we can see inside places like this dusty cloud where there's a star being born as we speak. Right in the middle, you can barely see it at the moment. Let's see if I can get my laser pointer to work. I'm going to make a laser pointer and then come back to this. So here in the middle, we've switched to the infrared view of this object. So now you can see there's a star right in the middle. It's got jets of material coming out. So this is quite typical of what happens when a star is born. And we use the infrared capability to see through the dust cloud that was blocking our view. And so that's number one, see through opaque clouds of dust. Number two, to see things that are too cool to send out their own light. So this is the debris of a dying star. There are actually 5 stars in this center, and you can only see 2 of them. But this is dust mostly that we're seeing, and it's too cool to send out its own visible light. It's not hot, it's only cool. But we can pick up the infrared light that it sends out and get a lot of detail to understand how stars die. And this is important because when stars die, they send out their material back out into outer space, and it's enriched with the chemical elements all the way up to iron. Those chemical elements are what you see around you in the house, in the building, the chemical elements your body is made of. So that's a pretty important story to understand this part. Now, the other chemical elements, the even heavier ones, come from a different process. When stars die, sometimes they do it in a great explosion and produce the other chemical elements that are even heavier than iron. So here's a little bit more detail there in the center, and eventually we'll understand the chemistry and physics of how stars die and produce dust that will be recycled to make new generations of stars and planets and people. So pretty fascinating part of our history. And by the way, that's one of the reasons I always wanted to do astronomy. I wanted to know our history, to see where did we come from, how did the planets grow, how do we have the right elements for life right here on the surface of Earth. So this is part of this story. How do you get the chemical elements out of the star and back into a planet? So as the third reason for studying infrared light is that the universe is expanding, or another way of saying it is distant galaxies appear to be running away from us at immense speeds. And when we see that happening, we need an infrared telescope to pick up the light was sent out at much shorter wavelengths. So that's why we built what we built, to see all these 3 different kinds of things. And what have we seen? Here is the first data release. We put it out on July 11th, almost 2 years ago now. And we see in this picture 3 different kinds of objects. You see this. These are ordinary stars, the bright objects with 6 spikes sticking out and another couple of fainter ones. Those are ordinary stars, and they're not that interesting anymore because we know a lot about them. In the middle, we have some very big, gigantic, fuzzy objects, and those are huge, huge galaxies with way over 100 billion stars in them. And those are also ordinary as far as we know, but they're important to us because they have so much gravity that they can bend light from the even more distant universe around them. So then you see these funny curved objects that sometimes you see them in pairs. That one is a almost mirror image of that one. That's a mirror image of that one. So these curved, strange pink objects are actually images of much more distant galaxies. They're pink because the light has been stretched out by the expansion of the universe, and they're magnified by the lenses that nature gave us through gravitation. Einstein predicted this would be true, and it is a remarkably powerful tool. We have hundreds of these in the sky that we know about, and we know where to point to find out something interesting. So the light from the early universe has actually been bent by quite a lot by the time it gets to our telescope by the forces of gravity. So sometimes by 1 or 2 arc minutes. An arc minute is about as small an angle as you can see with your eye. So you wouldn't be able to know if you didn't have a telescope, but we do. And so these images should have been way over there or somewhere way over there, and they're in the wrong place because of the gravitational force of these big galaxies in the middle. So what have we found out about the early galaxies? Well, we did not understand them. That's the most important thing. We thought we knew. We had theoretical predictions. We had measurements. We had all the pictures we took with Hubble. We had good reasons to think differently, but we were wrong. And that's one of the fun things about being a scientist. You discover that we and our friends and colleagues have been wrong for a long time, and there's something to do to really tease out the secrets of the universe. So how do we find them? Well, we look for a funny, small fuzzy object with the colors that tell us that it's from the great distances, and then we stretch out the light into a rainbow and measure the details of it and tell you the story about it, what's in it, and how it's moving. So that's number one. They were not what we expected. And we even seem to see that they are long and stringy, and they are not round when they're young. So they're still in the process of being formed. And it is just a pretty new discovery this year. And I have a movie to show you. I hope it shows up on your screen. This is a simulated early universe. In the computer, they put in random hot and cold spots as we measured from the Big Bang picture. And then they said, okay, we know the laws of nature, or we pretend we do. Let them run in the computer simulation and see how the galaxies grow. So they've got a box of early material, and they're rotating it in front of our eyes, and the clock is ticking and the galaxies are growing. So, of course, they've taken out from this observer's perspective in the computer, they've pretended the universe is not expanding for the picture, so you can see that. Otherwise, everything would have been flying rapidly apart. Now, in this picture, around 3.5 billion years after everything started expanding, we begin to see vast numbers of explosions. These explosions are groups of stars suddenly exploding when they get to be old enough and they've reached the limit of all the fuel. They burn out explosively. So huge amounts of energy are being sent out into the world, into the universe, blowing holes in the galaxies that they're in. So here the age of the universe in this picture is now 7 billion years. And the solar system hasn't even been born yet at that age. Solar system turns up when the universe is about 9 billion years old, 2/3 of its current age. So imagine somewhere in one of these little fuzzy dots, which is an imaginary simulated future galaxy, there is a solar system growing. And then wait a little while, and then the Earth would finally grow around the sun in that imaginary place. So I think it's a beautiful movie. It's a way that we have to understand how things progress with time, even though we can't live for 13.8 billion years to see it happen. So there is a story of the expanded universe turning into galaxies. So what else have we seen? Well, we always wanted to know what came first. There are actually two things that could have come before the galaxies. One is a black hole. It's possible that black holes were already in existence in the early universe. The other thing is galaxies have hundreds of things called globular clusters. And so we've been able to see in this most distant one, as magnified by one of Einstein's gravitational lenses, that there are hundreds of globular clusters in this very early galaxy. So looking back in time, we will eventually be able to tell you how did the galaxies grow. Here's a pretty astonishing picture. Also, there's these lenses that Einstein told us about occasionally have unlimited magnification. There's a curve that's called the lensing critical curve, and if there's a star right behind it, it will be magnified by thousands or tens of thousands of times, so we can see an individual star at immense distances. Another pretty picture to show you here is a collection of 5 galaxies. The one on the left in the middle is pretty near to us, and we can even see individual stars, depending on how good your computer screen is, individual stars in that galaxy. The 4 on the right are close together to each other, and they are in the process of merging together. In a few 100 million years, they will fall together and become a single galaxy. The debris from a collision is shown in the kind of pinkish colors here. This gas has been expelled from the colliding material, and new stars are being born in that colliding material. So we also have a laboratory in front of us to see how do stars get formed in a galaxy. Here is another remarkable galaxy. This is called the Cartwheel Galaxy for the fairly obvious reason that it looks like one. The story here is that a galaxy went straight through the middle of the big galaxy, and the collision debris is flying outwards and making that bright ring. So gas was expelled from the center. It was compressed and enough so that a new generation of stars could be formed in it, and we see them as they are there, all flying outwards from the center of that shocked galaxy. Galaxies can have holes in them. If you observe with infrared light, this is what seemed to be an ordinary spiral galaxy. But when you use the infrared light from about 10 micrometers wavelength, 5 to 10, we see a rather different picture. This is the light that comes from the dust itself in a galaxy, and we see that there's a hole. There are many holes in this galaxy that make it look like a sponge, a slice through a sponge. So where do the holes in a sponge come from? They're made by gas pressure when the sponge is manufactured. The holes in the galaxy come from something similar. A burst of stars exploding over here in the middle of this hole, maybe 100 million years ago, have blown a hole and pushed away the material, which is now in this ring shaped around it. And you see there are many holes all over this galaxy then. So this is a typical result. We didn't know it at all before we had this picture. And by the way, this is the result of a amateur person. Her name is Judy Schmidt. She lives in Modesto, California, and she takes NASA images and improves them by changing the colors a little and stretching the contrast so you can see the features even better. Here is what we used to call the pillars of creation. I think we still call it the pillars of creation. This is a cloud of material where the stars are being born today. What it looks like is actually true. There's a wind blowing through space from the top right to the lower left, and is shredding and destroying the cloud of dusty gas that you see here in the middle. Some of it is evaporating from the surface. You see a sort of glowing blue area around it. You see a brand new star that's just been born in this very dense little corner here. Many more stars are being born in similar ways in these compressed regions. There's even a zone where a particular chemical is being seen shining out through the dust cloud. This is a chemistry laboratory for us to understand how are stars like the sun born. And here we have hundreds and hundreds of them happening before our very eyes. Here is a picture of a star seen as it's forming with its solar system, with this whole collection of planets and other things growing with it. So the typical picture that we have is a star is born from a rotating cloud of gas and dust, and it ends up in a pancake shape. So we're looking edge on at the pancake. So the star is right in the middle, and the pancake goes here, and it's opaque because we're looking at it edge on. We cannot see the star in the middle. We can see the stars shining upwards and downwards. And if you were to come back in a few 100,000 years or a million, this cloud of dust would go away, and we would be able to see the individual planets orbiting around that star. Right now, it's a subject for calculation and interpretation, so eventually somebody will have a story to tell you about how this one is really working. We have had some interesting surprises. We generally think that planets form in orbit around stars, but we have found many examples that they don't. These are Jupiter mass objects, and they form in pairs without the benefit of a big star. We've seen dozens of them here in the Orion Nebula. We have been examining planets to see do they have an atmosphere? And this particular method is done by waiting for a planet to go in front of the star. And if you wait long enough and watch enough stars, you will see that many of them have planets that pass in front. And if they do it over and over again, you can say, well, okay, I know how long it takes to go around. I know about the star. I can calculate how massive, well, I can calculate how big is the planet and what its temperature should be. Even if I can't see that, I can calculate it what it ought to be. And now I look to see, does any of the light of the star go through an atmosphere of the planet? And if it did, then the planet would appear to have a different size according to wavelength. Clouds in the upper atmosphere of a planet would block more light than at other wavelengths where the clouds were transparent. So we've examined many, many, many. Even in the first year, we had 6 to look at, including 24 Earth-sized planets orbiting these small stars. Now, the good thing is that we can do this, and we have measured what we expected to measure. The technique works beautifully. All of the large planets have atmospheres, like Jupiter or Saturn or Uranus or Neptune. All of the small planets have no atmosphere, which is not really a surprise, but it's still a kind of a disappointment. The reason it's not a surprise is the technique is only working for a class of stars called M stars. They're very small, and they're very active. They send out blasts of material into space that are quite dangerous for planets that are nearby. And so there's a lot to say about that, but we have not yet been able to look in the right place to see if there could be planets that are really like Earth. So don't give up yet. Come back again when we have the better equipment even than this. So we've been looking at things in the outer solar system. Here is the great planet Jupiter. It doesn't have its red spot because it's a blue spot. When we make our pictures, of course, we have to give them artificial colors. We have to give them colors that mean something. So usually what we do is the same thing that we do with our human eyes. The short wavelength is blue, the long wavelength is red, and in between we have yellow and green. So Jupiter is beautiful as always. It has the giant red spot, which is a mystery forever. It's been this giant storm there on Jupiter for 400 years, ever since Galileo first saw it. Fascinating thing to understand, and important also for the story of how the Earth was formed. When we look for other solar systems, we are looking for something similar to our own, and so far we have not yet found any solar systems like ours. We attacked an asteroid. We dropped a piece of metal onto an asteroid to see what would happen. And it's not just for fun, it's to learn about how to protect the Earth from killer asteroids. And every now and then we get a big one, which is quite dangerous. In Arizona, there's a crater 1,000 feet across, which I remember seeing as a child. In more recent times, there was a meteor that flew over Chelyabinsk in former Soviet Union, and a lot of people died because of the shock waves that came out of that object. So we do need to protect ourselves from asteroids, not just the very rare ones that would wipe out all of life, but also the ones that would hurt a city. So we've learned how to do that. We've been taking pictures of Titan. This is a satellite of Saturn. This is the satellite, the only big satellite in the solar system that has its own atmosphere. So it's got enough atmosphere to fly a helicopter. So we are going to do that. The Dragonfly helicopter is supposed to land in 2034 and look around on the surface. The surface has rocks, which are basically water ice, and it has lakes, rivers, clouds, and rain, which are due to hydrocarbons, ethane and methane. What you would use for fuel here on Earth is just ordinary liquid there. Is there a possibility of life based on that? Who knows? But at any rate, nature has done the experiment here to set up the conditions where if there's another kind of life possible, we would look here to see if there's a sign of it. We have a picture of Uranus, one of the other outer solar system planets. Here we get a picture of the rings almost face on, and it's possible because the spin axis of Uranus is actually close to being in the plane of the orbit. So, once every orbit, we'll be able to look straight at the pole. So a beautiful thing to understand, again, to help us think about the formation of solar systems and whether our solar system is unique. So maybe we'll wrap up here and have questions. There's always much more to talk about, but let's stop here and I'll stop sharing my screen and we can talk about the questions that you all have.
Wow, thank you, Dr. Mather. That was fascinating. I'm a little crushed that ET isn't out there, however. But if you'd like to ask questions, you could raise your hand or put it in the chat, whichever you prefer.
Yes, and I am watching the chat so I can see you. Just type away.
I think you wowed us.
See, Doris Belinsky is waving her hand.
I have a question, and I don't really quite understand. I think you've given us a wonderful presentation. Thank you. And it's amazing what Hubble is showing us. Waiting now for the Roman telescope, although I probably won't be around anymore when that's up, because I knew Nancy Roman. She was a member of my AAUW group. But my question is this. You're talking about the expanding universe. What did it start from, and where did the matter come from that started the whole Big Bang, or whatever we want to call it? Because that's the puzzle to me, you know. It's all very growing, but it's got to come from something.
Yeah, well, you and me both. There is actually no convincing story about what really was the reason for that to be. In other words, what we do see is that the universe is infinite now, apparently. There's no perceivable edge. There's no perceivable center. So we imagine that it was always infinite. So whatever was in the early times was quite incredible, quite unimaginable. many thoughts from theorists have come along. There's something called inflation theory, which guesses that there is a kind of quantum mechanical process in the early times that causes the expansion, and then as it decays and disintegrates, it produces all the particles that we know about. So that's a story which does actually hold together, but it just pushes back one step towards the one more layer of turtles, you know.
So you're saying that there's something that it started from something. I mean, that must have been something very dense. But you're saying,
Yeah, it was extremely dense when it was young, and when it was very, very young, it might not have even had any of the particles that you know of today. So before protons, electrons, and all those things, something else. And it's just a guess, but it seems to fit.
okay. And then you say the fragments that are falling apart would cool down again, and so we'd have a renewal. Is that possible?
That is a possibility. It's a popular thought. Right now, it looks like the universe is accelerating and going faster and faster all the time. So that does not sound very much like it's going to turn around. But we don't know why it's doing that, so we don't know why it can't stop either. So it's a very popular idea that the universe is bouncing from a prior version.
Thank you.
Let's see.
What will the Roman telescope show us that Hubble can't?
Okay. Nancy Grace Roman Space Telescope is coming in about 3 years, and it's going to survey a very large fraction of the sky to look for evidence of the dark matter and the dark energy. So you can't see them, but you can see evidence of them. And if you get measurements of hundreds of millions of galaxies, then there's enough evidence to calculate something. So that's the sort of number one objective. Of course, if you're going to survey that much sky, you sort of hope to see something unusual. So it'll be a kind of finder chart for the Webb. And there's one new thing that we're carrying on board, which is a device specially to see planets. It's called a coronagraph. We're going to have an eclipse of the sun on April 8th.
I know I'm going to
And so you can see the solar corona. So people said, well, we don't wait for an eclipse. Can we build a coronagraph so we can see the solar corona any day? So that's called a coronagraph. And then we said, well, if we make a good enough one, we can put it in space and see planets orbiting around another star. So that's the objective of that one. So those are the three or four big things the Nancy Grace Roman Space Telescope will do. So coming soon, only 3 years or so.
That's amazing.
And since we're on the topic of new telescopes, let me add that we have ambition to do something even more powerful. And after that, we don't have a plan or a design, but we do have an objective that's very popular, which is please build a telescope that can see an Earth orbiting around a star like the sun. So, well, where is there life? We've got one example. So look for more places like that. And so that's the strong wish. And I think we have the support to do it, but it'll take a while.
Very interesting. Thank you so much.
Yeah.
I will be in Texas actually to see the eclipse. It'll be my first time.
Yeah, me too. I'm going there too.
Okay, maybe we'll meet there.
Yeah. Okay, more questions, please.
There's one, I'll just start from the top. How has the Webb changed our understanding of dark matter?
So far, we haven't had to change our opinion about dark matter much. We're using it as a tool, but we've not heard any major discoveries about it. The trouble with dark matter is you can't see it. All you can do is see the gravitational effects. So people are working on it, but no big surprises yet.
This may be the same question in a sense. Are there new results from Webb that bring doubts about the reality of dark matter or dark energy?
Good question. No, not really. Um, they well, a lot of us think, who asked for that? That can't be right. And nobody's ever seen any sign of them anywhere else. So astronomers are the only ones that have evidence. Um, but no change on that one.
Next question is, why does the Webb telescope have to be kept cold? You mentioned that often. Wouldn't the coldness of space be enough?
Yes, well, so yes, it has to be kept cold so that it doesn't emit infrared light. So you sitting there, you're transmitting about 500 watts of infrared power right now. And so if the telescope were warm, it would be transmitting infrared also. So it has to be cold so we don't pick up the infrared light from the telescope. And we do have one of the instruments that has to be even colder than the others so that it has its own refrigerator.
Let's see. Are there chemicals that, if found in an exoplanet atmosphere, would be a clear sign of life, metabolism, etc.?
Well, that's a really hard question. If we ever find them, we're going to have an argument more than a discovery. But clearly the most popular thing to hunt for is oxygen, because here on planet Earth, it's made by photosynthesis, and it's extremely reactive. So it all disappear very quickly if the plants stop doing what they're doing. So that's a very strong bit of evidence, but once you see something, you still get to argue about it. It would be such an important discovery that everybody will have an opinion for a long time.
I see a hand up. That's Malka. Malka, do you want to unmute and ask your question? In the meantime, let me go to another one in the chat. Somebody asked if there were books that you might recommend that we could begin to begin to understand. Malka, if you don't mind waiting just a minute.
Okay.
Are there books that are more elementary that we could, those of us not physicists, I presume, could begin to learn more?
I haven't actually tried to choose one recently. Some of the most readable ones are by an Italian physicist.
Must be.
There's something called 7 Brief Lessons in Physics, which is just a really sweet little book. By Carlo Rovelli, Rovelli. So I like his books. He's got many.
Thank you. Malka, do you want to ask your question?
Yes, it's her husband who wants to ask the question. What is the probability that right now there are planets in the universe capable of supporting sentient life like ours?
Well, since probability in this interpretation would be a personal opinion, I think it's 100%. So the reason that I think that is I agree with the idea that life is a thermodynamic imperative that will always occur. On the other hand, I think that our particular kind of life is going to be very rare. So I expect there would be well, about 20% of the stars that we know of have planets the size and temperature of Earth. Close enough. So on the other hand, it took all of time for us to get here. We're rare. Even in the history of Earth, we are very rare. So I think it'll be rare, but the universe is large.
Thank you.
The next question is right on with that. The universe is infinite. Can you please expand?
Oh, hi, Jim. Yeah. Of course, we can't really prove that the universe is infinite, but since ancient Greek times, we realized that there's no such thing as the largest number, because if you had one, you could always add one and it would be bigger. So they were shocked with this discovery. They also recognized that although you can't see very far always, there's no sense of coming to the edge of things. So that's about all there is. I can tell you that there's infinite is not a thing. Infinite means without limit. So that seems to be what we have. We have to guess about the part that we can't see, because the universe does have an age. So that means you cannot see the whole history of the universe at all places. You can only see different pieces in different places. So anyway, that's our challenge. We obviously have to make a guess about the part that we can't see.
Carter just put the book you mentioned in the chat, Seven Brief
Yes,
Lessons on Physics.
Yes, that's him. It's wonderful.
Bonnie, I don't understand your question. You mentioned the dichotomy of wave versus quantum physics.
Yes. Well, okay. Yes, I did mention very briefly. It's a wonderful mystery. We know that light behaves as a wave because it bends around corners and does something called diffraction, and we make instruments based on the wavelengths. And nevertheless, when it arrives and interacts with chemical things like your eye or a device, and we might want to get an electron from it, it behaves as though it has particle nature. So this is a very deep challenge for our understanding, and but just it's something we just look at and we have to say, okay, that's how it is. I don't understand it. It seems completely not intuitive, but it is how it behaves.
Did you have more?
John,
Yeah.
I'm Mike McClellan, and
Yeah,
I the other half got lost. But
Okay.
is there any possibility of a resolution of this dichotomy, of this understanding, and would it have any effect on cosmology and your ability to observe?
I think we're just sort of stuck with our opinion that it doesn't make any sense to us, but the universe doesn't have to make sense to us. We just have to figure out what it does. So I don't think we're going to get any escapes from the current troubles by resolving that, but you never know. The quantum recognition is so strange in a very deep way that we don't quite appreciate it yet. So
Thank you. Yeah.
I think there's a lot of surprise in this territory.
Okay, I know it was an impossible question.
Yeah, just by the way, as a reminder, everything you see around you is quantum in nature. All of chemistry relates to the quantum mechanics of electrons.
Uh-huh.
So your body is a walking demonstration that quantum mechanics works, but it doesn't feel like it, does it?
All right. Thanks.
We have another question. If the universe has a finite age, then how can it be infinite in size?
All I can say is that's what we see, or every reason to guess. If you just take the universe that we have today and you imagine going outwards and indefinitely in every direction, there's no reason to think you come to an edge. So that says, well, it is infinite in space, and there is, but it is finite in age. On the other hand, you cannot get all the way back to time zero. You can only get close. If you try to imagine all the way back to zero, your imagination runs out of imagination. You just can't imagine that. So we can get close in our imagination, but not all the way at the moment. Some person, some year may say, I know how to solve that. I have a new theory that says what comes before time equals zero. And if we ever have a thing that we like and believe, then we'll have a new story for you.
Here's another question near and dear to my heart. What is your take on aliens and UFOs? People make claims that they have seen these things. What might they be seeing?
Well, good question. I think there's no chance that they're space aliens because the other planets outside the solar system are just too dang far away. You can't get here from there, and you can't get there from here. If you were to travel at the speed of light, which we can't, it would take you 4 years to get to the nearest other star. And if you travel at the speed that we can achieve, it's more like 100,000 years. So unless you imagine that there are some completely new discoveries coming in the nature of propulsion, then they can't possibly be space aliens. There are plenty of things we don't understand, so unidentified is a perfect description. So there's one of the stories I've heard that makes some sense to me is that when people first started seeing weird things happening in the Southwest, it was actually military things. And if you really want to confuse people and make sure they don't discover what it is, you say it's a space alien.
Following up on that, this might be straying more into politics than science, but do you have any thoughts on the benefits and risks of increased reliance on private sector companies for the U.S. space program?
Well, I would say we've been 100% reliant on them from the first moment. We put our NASA label on things, but we buy stuff from big companies. So the number of people, the number of civil servants we have working over at Goddard is only about a third of the total staff at Goddard. And when I said it took 20,000 people to build the Webb telescope, well, most of them were not here. Most of them are under contract to various big companies. So it's pretty nearly 100% reliance all along. We like to say we have leadership, we have the vision, we have the job of deciding what to do at NASA. And personally, I am thrilled to see the successes of private enterprise. The old line companies, like the ones that built the previous generations of rockets, they never would have bothered to reuse their launch vehicles, but Elon said he would, and he did. And now the others are copying.
Another question, you said the image of the Big Bang was not an ideal model to explain the event. Can you give us a better example of visualizing it mentally?
Yeah, let's give it a try. Let's say the universe is infinite now, and just visualize it with a sheet of paper covered with little squares, like you get in school, except imagine that it runs off indefinitely far in all directions. And then you say, okay, well, now imagine that this piece of paper is expanding by making all the squares bigger. So that's closer to the picture that we astronomers have. So if you establish one point, like you put a dot in one of the squares and say that's the center, then it looks like everything else is running away from the center. And that's how it feels to us. We see the other galaxies are all running away from us. But when you take the graph paper picture that I just gave you, and you imagine being at another square somewhere else, that one would also feel like it was the center to the people that were living over there. So we have an expanding universe that's infinite and has no edge and no center either. And now that's the expansion part. Now imagine running it backwards in your mind so the squares get smaller and smaller and smaller. And if there's matter in there, they get more and more compressed. Now, eventually you run out of imagination. And that's what we call the Big Bang, where you run out of imagination.
I don't see any other questions in the chat. Do you, Carter?
No, I don't right now.
Anybody have another question? Well, seeing none, Dr. Mather, that was fascinating. As somebody that could barely get through organic chemistry, even I understood what you were talking about. So I really appreciate your time, and that it really is just an amazing. It's amazing especially to think that we're the only life form. Does that leave out like viruses and things like that? That's life to a degree, isn't it?
Yeah, yeah, it is.
Good, maybe that good. Then we won't keep COVID out there.
Yeah, yeah. Well, maybe our future includes inventing artificial life that can travel to the other stars, but you never know. If you were a future intelligent robot, you could still say, "I'd rather stay home."
Well, thank you very much. There are a lot wonderful comments in the chat. It was amazing, fascinating. Thank you so much. It really was a great way to spend a Saturday afternoon. We thank you so much.
Oh, well,
And
thank you, Marianne. I'm glad to have a chance to talk with my friends and neighbors. So, talk with you again.
well, and everybody, I encourage you to look for the upcoming corridor conversations. We will send them out via our various sources. And as always, if you have suggestions of topics that you'd like us to investigate and find speakers, please let us know. We're scheduled through April, and then we'll be planning more for the summer. Thank you
Okay.
all for coming. Have a great rest of your weekend.